Start.
Yeah.
Okay. Good evening, all. I'm Deepa Vinod, Academic Council of MyQT. Welcome to our third section on quantum programming using IBM Qiskit. We are grateful for your wonderful cooperation and feedbacks, which is helping us for the betterment of the upcoming sessions. My Quantum Technology, MyQT, is your partner in quantum computing journey, providing innovative quantum computing training and solutions. MyQT is a repository of world-class knowledge and wisdom contributed by the best minds in the field of quantum computing. MyQT operates along the globe through its vast network of affiliates and partner organizations. MyQT offers training, certification courses, research opportunity, and consulting services. Now, it's time to proudly introduce our speaker, Mrs. Manjula Gandhi, Associate Professor, Coimbatore Institute of Technology. Welcoming you ma'am. Mrs. Manjula is working as an associate professor at Coimbatore Institute of Technology for the last 22 years and IBM Qiskit advocate from September 2020, an IBM quantum educator, an IBM certificate associate, developer quantum computing using Qiskit. Working in the area of quantum computing from 2003 as a part of her MS and PhD. Her research interest includes building reversible circuits, quantum machine learning, and quantum games. She's teaching quantum computing for the last 3 years at Coimbatore Institute of Technology. Once again, I welcome all the participants, and now I hand over to Manjula ma'am. Thank you.
Thank you, Deepa ma'am, for the sweet introduction. And KG, thanks a lot for your invitation. And let me share my screen and start the session.
Please go ahead.
So I hope my screen is visible. I welcome all the participants for today's session and wish you all the best. And I hope you will take something out of my session today. KG, shall I start?
Yeah, yes, Manjula, you can start.
Yeah. So my today's agenda is why we should contribute to quantum computing, why we should learn, and how are we transiting from our classical bits to quantum bits. We'll see an example. And the next part of my talk will be the circuits behind quantum systems. So we'll be looking into reversible circuits, and we'll also have a glimpse of all the quantum gates which are available. We'll be talking about single qubit gates and multi-qubit gates, and the various visualizations which Qiskit supports actually, and how to run a job using real devices and simulators, and I will share some of the references. So moving on, why we are into quantum systems. Actually, we know the transitions, actually they are first generation computers, second generation, third generation, and so on. So what is quantum computing? So quantum computing, actually we are now looking at our devices which are reducing in size. So one thing is we have smaller devices, and the speed and the memory capacity of our devices in current day has become huge. So the thing is, what will happen if it goes on miniaturizing in such a way, in such a thing? That is the end of Moore's law. So what will happen, or how will it come into a rescue of when we are moving on? So the thing is, quantum computers comes into existence and will help us solve our current problems. So the main thing is our systems are, we lose data in our classical computers, since the circuits behind our classical machines are irreversible in nature. That is, we don't have a one-to-one mapping between our inputs to outputs. When we compute something, we go from input to output, and the reverse direction, that is from output to input, it is not possible for us if I am using a classical machine, that is our current day computers. But the thing is, if I'm using a quantum machine, we can walk in both the directions. That is, we can transit from input to output, and I can also go back from my output to input. So the idea is we're not going to lose any data, and since we don't lose any data, the heat dissipated will be very less in case of quantum computers. So these are some of the advantages why we have to move on. And the properties behind quantum machines are, we have the very important property called as superposition, where I can compute on multiple values at the same time, first one. And the second one is entanglement. I can entangle two qubits, and looking at one qubit, we can identify what will be the state of the other qubit in another universe actually. And the third property is interference. So these properties help us to learn and contribute more into quantum machines. So in my slides, I've given about the miniaturization of integrated circuits is going to be a major problem actually. The sinking transistor sizes and power dissipation are the major barriers in the development of smaller and more powerful circuits. But reversible logic helps us to go for overcoming these problems, where we'll have zero power dissipation if only if our circuits are reversible in nature. That is, if I have a
Madam, I'm seeing only the quantum programming using IBM Qiskit, the first slide. Is it for me only or for others also? I'm not sure.
KG, can you check this? I'm actually moving on. Is my screen not visible?
Your screen is visible, but I'm seeing only the first slide.
Yes, KG, it's remained the same screen, the first screen.
Yeah. Yeah, now I'm seeing introduction.
Okay, let me share my screen now. Can you see me? Check it now.
Yeah, your screen is being shared. We are seeing PowerPoint, the slide, introduction slide.
Moved on to my slide number 4. You're not visible. It is not visible for you.
Now, no, we are seeing 3. Slide number 3. I'm seeing slide number 3, and then it is not in the presentation mode.
It is in the presentation mode only, sir.
Then I think you have to change the windows, sharing window. Actually, we are seeing other PowerPoint window, not the presentation window.
One second.
Can you stop and share the presentation window again?
1 second. What about now? Deepa, is it visible?
No.
It's not visible, ma'am.
It's not visible. Yeah.
I've opened my share screen. I've gone into my PPT.
In PPT, there are 2 windows, right?
Actually, no, I have only one view of my PPT here.
Yeah, this one, it is appearing as a slides, not in the show mode.
This is in
now
slide.
we are seeing slide number 5.
Yeah, but if I go for sharing my screen from this, that is, I can go from current slide, right? I'll go with this. But if I go with this, I think you're not able to view it. Check this now. Can you see my screen number 4?
No, still it is 3.
3.
So what, after sharing, you have to go back, stop sharing, and then share that presentation slide. Yeah, because once you start presentation, it will open in another window, I believe so.
I'm not able to.
Visible now.
Deepa ma'am, can you help me in this? I'm on this slide. I'm actually shared already. So if I'm stop sharing.
Okay. After when you share again, select the window. At that time, you will see 2 PPTs.
Like I'm able to see, if I don't share it there, I'm able to see only one PPT.
Or else without presentation mode, you can just go ahead. That's also good.
Fine. This view looks fine, right?
Yeah. This also will work. Yep. Yeah, this is working. We are seeing now. We are third slide 3. You can proceed this way also.
4.
Yeah.
Yes.
Please go ahead. Yeah. Okay. Thank you.
We were talking about reversible circuits will have zero participation. So that is why we are into quantum machines. So quantum computing benefits from reversible descriptions. So we go for why? Because every quantum circuit is inherently reversible in nature. We'll have a one-to-one mapping between our inputs to outputs and output to input. So what is a quantum computer? It is a type of computer that uses quantum mechanics principles so that it can perform certain kinds of computations more efficiently than a regular quantum computer can. So in our classical machines, we use a concept of bits where we can either be in 0 or 1. But whereas in quantum machines, we'll look into something called as quantum bits, and we'll call them as qubits. Qubits are like we are not going to be, this is classical system where we have state 0 or state 1. So at a particular time I can either be in my state 0 or I can be in my state 1. Whereas when I'm talking about a quantum machine, it is not possible for us, like here we'll be in, this is my state 0, this is state 1, and we can also be in a superposition of both the states. What do I mean by superposition is a qubit can stay in 0 and at 1 at the same time. Okay, so this is the advantage of moving into quantum computations. So here in a classical machine we have our data units as bits, whereas in a quantum machine we have them as qubits. So an upward arrow denotes it is state 0, and a downward arrow denotes state 1, and this is in the superposition state. We'll have a block sphere representations. There are many various visualizations which Qiskit supports that we'll see it later. So a valid state xi can be given by, we read this the form of ket notation, C1 ket 0 plus C2 ket 1, where your sum of the squares of the amplitudes, that is mod of C1 square plus mod C2 square, should sum up to be 1. This is a valid state. Only if this particular sum of the squares of your amplitude sums up to 1, we call those states as a valid quantum state. So the idea is we are into reversible circuits, and we'll be using quantum mechanics, the Prat notation, for representing a quantum state. As I'm just giving a scenario here of a travel agency. Say for example, we are running a travel agency where we have 2 cars and there are 3 persons. So naming them as A, B and C, and I've denoted some of them as friend pairs and some of them as enemy pairs. So I have A and B are friends, A and C are enemies, B and C are again enemies. So there are 2 taxis. The idea is you have to use these 2 taxis, and you have to these 3 people have to travel these via these 2 taxis. So the thing is, if we go with a friend and an enemy, our trip is not going to be a happy one. So we want the friend pairs to take one taxi and the enemy one to be in another taxi. So the configuration here we have is, I'm taking ABC. If it is 0 means all 3 ABC are in state 0, indicates that all three are traveling in taxi 0. When I take 0, 1, 1, it means that B and C are traveling in taxi 1 and A is traveling in taxi 0. So this 0 denotes taxi 0 and the 1 denotes taxi 1. So what are we actually doing here? So we are calculating a configuration score here. What do we mean by configuration score is the number of friend pairs sharing the same car minus number of enemy pairs sharing the same car. This might be very small in size. The score of the configuration is given by number of friend pairs sharing the same car minus number of enemy pairs sharing the same car. So how do we calculate this? Say for example, if I take 100, B and C is enemy. B and C are enemies. A is traveling in taxi 1. So the number of friend pairs minus number of enemy pairs. So we have one enemy pair and one. So it is 0 minus 1. So for 100, we'll have it as minus 1 as our configuration score. Where because A is traveling in taxi 1, B and C are enemies, they are traveling in taxi 0. So the number of friend pairs, we don't have any friend pairs, so 0. minus number of enemy pairs, we have one enemy pair, so 0 minus 1, our configuration score is -1 here. Similarly, if I take for A and B are traveling in taxi 0 and C is traveling in taxi 1, so this case 0, 0, 1, our configuration score is going to be 1. The other positive cases, if A and B are traveling in taxi 1 and C is traveling in taxi 0, we'll also have a positive configuration. So the idea is if both A and B travel in the same taxi, our configuration score will be high, otherwise our configuration score will be reduced. So we have to, we would say the solution for this particular scenario is 0, 0, 1 and 1, 1, 0 will give us the best solution in this particular example. Here we had 3 people in 2 taxis. Say if I'm increasing 4 people, so there are 4 friends now, and again we are having 2 taxis. So the number of configurations we have is 2 to the power 4, that is 16 different ways we'll have. So all 4 zeros, all 4 ones, all various configurations which we'll have. So here we can write a small program, a classical program to compute this, and we can calculate this configuration score. Number of friend pairs, say if here in this case A and C are friends, B and C are friends. So if A and C and B and C are traveling in the same car, we'll have a highest configuration score, otherwise we'll have negative scores. So we'll choose a score which gives us highest one. So that is going to be our solution. If I'm taking it out to be 2 to the power 4 different combinations here, that is 16 different ways. What will happen if I'm doing it for 100 people? Instead of taking taxi, let me take a car. So in 2 to the power 100 configurations, we'll have, if there are 100 people, we'll have 2 to the power 100 different configurations, where we'll have 1 million configurations, which is impossible for us to solve on a regular classical machine. So if I'm having 3 people, we had 8 different configurations. If I'm having 4, we'll have 16 ways. If we are having 100, we'll have 2 to the power 100, which is impossible for us to solve on a classical machine. So what we can do, can I solve this problem using a quantum machine? Yes, quantum computers give us an option of computing on multiple configurations on a single run. So if I am taking about a single qubit machine where we can compute on 0 and 1 at the same time. So if I am talking about a 2-bit machine, 2 qubits, so I'll have combinations of all 4. So 0, 0, 0, 1, 1, 0 and 1, 1. I can compute on all these 4 configurations in one run of your quantum program and compute the values here. So this was our 3 people traveling in 2 taxis, 8 different configurations. So 0, 0, 0, 1, 1 was one best solution. The other one was 1, 1, 0 was another best solution. So we have 8 different configurations here. And if I'm using a classical program, as we saw earlier, we'll have 2 to the power 8, there's 8 different, 2 to the power 3 different configurations here, and we have to compute on each of these configurations scores separately. But if I'm using a quantum machine to solve this problem, I can compute on all these 8 different values at the same time. So I can compute on 0, 0, I can find the configuration score for this. I find configuration score for 0, 0, 1. Similarly for 1, 0, 0, 1, 0, 1, and choose the one which gives me the best solution, which gives me the highest configuration score. So that is the idea why we are moving on to quantum machines. We can compute on multiple values at the same time because we can put in these 3 qubits in a superposition state and compute on all the values at the same time. So our travel agency problem will be an easier one if I'm using a quantum machine for solving it, because it executes on parallel universe. So this is a principle which we talk about called as superposition principle, where I can compute on 0 and at 1 and on 1 at the same time of our code. So the operations taken for computing our travel agency problem, if I'm having 100 different people traveling in 2 different buses, we'll have 10 to the power 30 computations operations, whereas a quantum machine will take only 1 computation for computing it. So we just run the problem using a quantum machine, and with one single operation, we can find the solution of our travel agency problem. There are drawbacks of quantum systems. They are actually prone to errors. Why? Because in reality, there are errors when running on a quantum program, when running a program on a quantum machine. So instead of finding the best solution, sometimes it might find the best, second best solution, third best solution, and so on. So what we can do for solving this particular problem is, we are going to run the same program for multiple iterations. Say, for example, I can run it for 1024 shots, 8024 shots. So if it is a real problem which we are taking on, you can run it for more number of shots and find out the best results from the results which we get. So the advantage of using a quantum machine is, the principles are, we have superposition principles where we can compute on multiple values at the same time. And since they are prone to errors, we are going to run the same program for multiple iterations. That is increasing the number of shots of your program, the running time of the number of executions. So it is still better for comparing to a classical machine. It is still better for us to invest our time on quantum machines. We can go for everything, any classical ideas which we are working on, your graph theory problems, your machine learning problems, your search techniques, all have a quantum counterpart actually. So we can move on. Anyone is interested in moving on to quantum can take their own area in classical computers and move on, find a counterpart in quantum computers. There are quantum compilers available. There are many quantum algorithms which are available for running out your problems, which you can solve them. All your design and analysis of algorithms like backtracking, your 8 queens problem, everything has a quantum counterpart actually. So that is why we are moving on to quantum machines. So in short, a comparison between a classical computer and a quantum computer. Quantum machines calculates with qubits, where we can represent 0 and 1 at the same time, whereas classical machines work on transistors which can represent either 0 or 1. So that is, I can either be in state 0 or in state 1, but here we can be in both the states. Next point is, your power increases exponentially in proportion to the number of qubits. Say if I'm working on a single qubit machine, I'll have 2 values. If I'm working on 2 qubits, we'll have 2 to the power 2. If we are working on 3, we'll have 2 to the power 3 different configurations, 2 to the power 4. So the power increases based on the number of qubits in a quantum system. Whereas here it works in a one-to-one relationship between the number of transistors here. The third point is quantum computers have error rates, very high error rates, and they have to be kept ultra cold. But whereas we all know classical machines work in room temperatures. So everyone are having devices now right at home. Maybe in quite to 10 to 15 years, we'll also have quantum computers as we have classical computers in current day. And the problems which are best suited for quantum machines are, we can work on with optimization problems, data analysis, unstructured searching, and simulations. So basically, I work on the circuits part of quantum systems. That is one. And the next, I started working on quantum machine learning, quantum graph theory problems, and I'm currently moving on to quantum compilers also. So there are many exposures, many ideas for us to work on. So only idea is, you have to be confident, patient, and to take a problem and solve it using a quantum machine, comparing it with the classical machines. So the next portion is, I'm moving on to reversible circuits. So what do we mean by reversible circuits and irreversible circuits? This is our irreversible AND gate, where we have, if the value of A and B is equivalent to 0, it is impossible for us to say what your A and what your B was, because either A can be 0 or B can be 0, or A can be 1 or B can be 1. Now if my output is 0. So this is the case which we have in our irreversible AND gate. Whereas reversible AND gate, here we have one-to-one mapping. So I have my A and B values are retained, and the third qubit gives me the value of A and B. Here I'm losing the value of A and B after obtaining the output of A and B. We lose our inputs. So irreversible circuits, we cannot have a one-to-one mapping. We cannot walk from outputs to inputs, and the idea is, the drawback is, we lose our inputs. So and these data loss are generated as heat, and which are dissipated. Actually, Laundrer and Feynman said that the loss of heat is actually going to be a major problem. This can be only solved only when your machines use reversible circuits. So reversible circuits will not lose any information. You will have a unique input-output vector, that is one-to-one mapping between our inputs and output vectors. Okay, so this gate, I'll come back to this after teaching quantum gates actually. And there are various quantum computing frameworks which are available. The first one is I prefer, and for today's session also we'll be looking into Qiskit actually. So IBM's product. Next is Q-Sharp, Microsoft's. Strawberry Fields and Penny Lane are of Xanadu's. And Cirq and TensorFlow Quantum are from Google. And Quantum Simulator is QSIM, which is being provided by our India. And next we also have a new one called as Classic Platform. All these are open source and anyone are interested to work on. If you're interested to work on machine learning, I would say Cirq and Penny Lane will help you to move on to machine learning concepts. So running an algorithm on quantum computers involves the following steps. So here from now on, I'll be moving on with IBM's Qiskit, how to work on a circuit using Qiskit. So the first thing, there are three things which we will be doing here. The first one, specify the number of qubits. So the number of qubits we have to give, and the next step is what are the combination of gates for making up your algorithm work to those qubits that we'll be giving. And the third part is measuring the qubits, and here we are going to store the results in a classical bit. Remember, if we go and observe a qubit, it gets collapsed. So what we do is we measure the qubits and store the results in a classical bits. So we need the quantum bits and a classical bit for executing a program on a Qiskit. This is a sample circuit here. So I have taken a 4-qubit quantum circuit, and this is your classical bits. So people who are new, assuming people are new here, so I'm taking Q0, Q1, Q2 and Q3 are qubits. There are 4 qubits here. Each qubit is separated, is shown in ones, different lines. And next is we have the quantum bits here. So this is a quantum circuit which takes 4 qubits and 2 classical bits. Classical bits are denoted using 2 straight lines. So this portion is your barrier. Just for user understandability, we have our quantum gates here. So these are gates which are operating on 1 qubit, and we call them as single qubits. And this particular gate is working on Q0 and Q2, so we call it as multi-qubit gates. So we have single qubit gates, multi-qubit gates, and this is my input portion. The same as we do in a classical program, you will have your inputs. You do some process, and the final thing is you measure it and you take your outputs. And this is your measurement symbol. We are measuring qubit Q2 and storing it in classical bit 0. This indicates the classical bit 0, the 0. And this one is you are measuring your Q3 and storing it in classical bit 1. Okay, so this is a basic quantum circuit here. Next is how to work with IBM's Qiskit. There are 2 ways in which you can run your programs. The first one, you can use an IBM Quantum Experience ID. You can just go into this particular site, create an ID, and you can work. Or the second one, you can install Miniconda in your machine, and then go for pip install Qiskit, install it, and you can start working locally also. So before going for the demo of the installation and all those things, I'm just checking out how a quantum state will be actually. So we are representing qubit states in a 2-dimensional vectors, where we generate a random quantum state qubit to be denoted as cos theta by 2 ket 0 plus e power I phi sin theta by 2. I read this as ket, ket 1. And there are 3 different bases here. The first one is Z basis. Next one is your X basis and your Y basis. I'll move to the next slide. It will be more clearer. Your Z basis, where we have your orthonormal, the state vectors are 0, ket 0 and ket 1. If I'm working on x basis, we'll call our states as plus and minus. So this is 0 plus 1. Your plus state is actually denoted by 0 plus 1 divided by root 2. And your minus state just opposite to it is given by 0 minus 1 divided by root 2. And your y state is 0 plus I1 divided by root 2, which we call it as I clockwise rotation and anti-clockwise rotations. Don't worry if you're not getting it. I'll be giving a demo of these states, how to create them, how to work on these three phases. So general fundamental introduction, we use bracket notation, direct notation here. We'll be representing states using vectors. So vector notation for state 0, this is important. For get 0, your vector is 1, 0. And for 1s, you'll write it as a 0, 1, 0, 1. And if it is a superposition state, that is, we'll have it as, if I'm taking it for plus, I'll be having it as 1 by root 2, 1, 1. If I'm taking it for minus, I'll be having 1 by root 2, I by root 2. Okay, this is for I, state I. This is not merely, it is not fully in 0 and not fully in 1, but a linear combination of both the twos. That is, get 0 and get 1, we have a combination of them and we call them as superposition state. The various backends which Qiskit supports is we have state vector simulator, CASM simulator and unitary simulator. We'll be using code for working on. So let me go with a demo of my quantum states. I just want to know if my screen visible or should I change my, don't I have a full screen option of sharing?
Yeah, no, Manjula madam, we are seeing only PowerPoint.
Yeah, once.
I think you have to share the entire screen. Or else select that MyQT, IBM Quantum Lab.
Oh, one second. Let me stop this.
Ma'am, this is Ravindra.
Yes, sir.
Ma'am, if possible, if you could able to share the code so that we can run in IBM Quantum, ma'am.
Yeah, one second. KG, I don't have an option of sharing my entire screen. Is it possible from somewhere else? Or the thing is, I have to go each and every time. I have to go and open it separately.
You are in browser or like Teams?
I'm in Teams thing.
So use Chrome tab, window. Which browser are you using?
Chrome.
Then it should show the three options. It should show in the top: Chrome tab, window, entire screen.
Is my screen visible now? Creating our first one.
Yeah.
Yes, it's visible now.
Yeah, it is visible.
Let me just change my tabs. Please check out. Tell me if it is okay for you. Now this slide.
Yeah, both tab. Yeah, this also we are seeing.
Everything is visible, right?
Yeah. I think we can continue.
Okay. All right. If I go for my PPT also, that is also fine, right?
Yeah, check now. If you're able to go to.
This is my PPT. Right now,
no, PPT is
no,
not visible.
No, PPT we are not seeing, ma'am, because I think you have shared only the Chrome.
The Chrome.
Correct.
How can I change it? Any options?
Ma'am, next to the mic button, you will be having a share button, right?
Next to
your mic symbol.
Okay. Yeah.
Camera, mic, and So click on to the share. And first option, screen, window, or tab will be there, right?
One second. Let me stop my screen. Open share tray. In my open share tray, I'm only able to get these sub options: Screen 1, Microsoft Teams, and all the windows which I have opened.
Yeah, and next to that you have a window and then you have an entire screen.
I'm not able to see that.
Ma'am, are you getting the option of choose what to share?
Yeah, that's
click on the share button.
Yeah, click that one. Click choose what to share.
When you click that, you will get 3 options, I think. Window, entire screen, and then your application which is opened. Chrome tab.
Maybe screen one will also do, right? I think.
Okay, anyways, let me just go with this and go back to my, when I'm going to my presentation.
Okay, yeah, you follow that method. I don't know why that is.
I don't know why I'm not
like this.
Anyways, okay. So my first demo for creating a first quantum state actually. KG, I just want to clarify if anyone is having any doubts till now.
I'm checking the chat window.
Yeah.
No questions. There is one question. No. It is for. There is question from Damini. Since we are measuring the output of quantum circuit in classical bits, are we not losing the actual final quantum state during measurement?
We do lose actually, because
yes, we are losing information.
We are losing information. That is one drawback. But the thing is, the idea, you have to go with your algorithms and just show you something else, and then we'll come back to this question. Okay. Right. So creating our first quantum state, I just want to show you how to create a state xi, setting it to 0. So from Qiskit, I'm importing these basic things. So we need quantum register, quantum circuit, and we'll be using R here and the execute function. So we are creating a quantum circuit of 1 qubit here. I'm not taking any classical bit in this example. And I'm initializing my state. If you remember, this is state 0 actually, your state 0. I'm calling my qc.initialize function for initializing this particular state. On this 0 indicates that I'm storing it, I'm applying this particular state to my qubit 0. And I'm drawing this function using qc.draw. And it initializes this particular state. I'm executing, as I told you, there are 3 different backends. One is state vector simulator. The other one is custom simulator, and we also have unitary simulator. This example takes state vector simulator as our backend. So we use our R server and we call get underscore backend function. And we are initializing, that is, we are telling Qiskit that we are simulating this particular circuit using state vector simulator, and I'm storing it in a variable called as backend. I'm now taking executing this function, this quantum circuit. So QC is my quantum circuit, executing it in this particular backend. So give your quantum circuit name and the backend which you have initialized here as a parameter to your execute function, and take the result, and I'm storing it in a variable called as result function. And I'm using another visualization here. The most important one which we use regularly is your state vector output. So I'm taking this particular result variable, result dot get underscore state vector, and I'm storing my output in an out underscore state variable, and I'm displaying it. So print of out underscore state. So what does it do? It displays me. We all remember we are in get 0. So get 0 was 1 0. But the output visualization of your Qiskit will actually be in a complex number notation. So this is A plus BI format, but Python uses, Qiskit works upon Python, so we use J here. So it is, the real part is 1 here, so 1 plus 0J, and for the 0 portion, we will have it as 0 plus 0J. So this is your kit 0. And we have various other visualizations. So I'm also showing this using histogram output. So one is state vector output. Your state vector notation output will look like this for kit 0. And for your histogram, we are executing it. And if I'm using state vector, we'll use get underscore state vector function, and we display the output in this form. But if I want my histogram output, we'll use get underscore counts function. So the same execute function, your quantum circuit and the backend, get the result, store it in a variable, and now instead of using get underscore state vector function, we are using get underscore counts function. So here I just want to measure how many times we were in state 0. That is, we are running this program, and this is where we execute it. We are executing a quantum circuit. For default, the third parameter given here is shots actually. If you don't specify anything, your quantum circuit will execute for 1024 shots. The default number of shots which your program will execute is 1024. If you don't specify, the default number of shots will be taken here. So I'm executing this particular quantum circuit for 1024 shots, and you could see for 100% probability we are in state 0. That is, all the time we have measured 0 because there was no change for us. So this is how you set it out and initialize it. Moving on to creating another state called as psi is equivalent to 1. So we have a quantum circuit here. I'm initializing it to get 1 now. So it is 0, 1. Again initializing it and drawing it using QC.draw function. And so executing it using get state vector function. So your state vector function is now going to be 0, 1. So it is 0 plus 0j and 1 plus 0j. This is how your output of get 1 will look like. Similarly, the histogram function. So I'm using get underscore histogram. It is enough if you import one-time plot underscore histogram, and you can call that function by passing the counts parameter of get underscore counts as a parameter to your plot histogram. And this time you could see your output is going to be for all my run, my output is going to be 1. So we have a probability of measuring 1. Full 100% probability of measuring 1. There is another method for creating get 0. So I just instead of initializing it by default, all qubits are initialized to state 0. So if you just go for creating a quantum circuit, executing it, I'm just creating a quantum circuit of one quantum register, executing my job hello underscore qubit, using the same backend and getting the result using state vector, and we get this 1 plus 0j plus 0 plus 0j. And this time instead of just a simple draw function, I've used matplot library as a parameter here. MPL stands for matplot library. So you can look at the circuit. Earlier we had that initialize box over here, but now matplot library uses a visualization, a more clearer visualization. So the thing which we have used is we have used quantum register, quantum circuit, AR, and execute function here. So AR is a classical simulator backend, and we are using AR provider here, and execute is a part of your AR simulator. And we are using your get underscore state vector function for it. Now, if I want to invert my qubit, say I have to just apply X gate. So what will my X gate do is it inverts it is just your classical NOT gate actually. So I'm applying 2 times X. So I've started with 0, applying X. So I'm moving on to 1. And again I'm applying X. So I'm moving on to 0. So what happens is it becomes neutralizes. So starts from 0, moves to 1 and moves back to 0. So that is what we have done here. So just looking at the code once again. So we are creating a quantum circuit of 1 qubit. The first parameter is qubit, and I'm applying X gate on qubit 0. Again I'm applying X gate on qubit 0. This is my circuit name actually. So hello underscore qubit is your quantum circuit's name. This can be a this is your user defined variable, you can have it anything. But once you create your quantum circuit with that particular name, use that circuit name. So hello underscore qubit dot x of 0, moving to state 1. Again I'm applying hello underscore qubit dot x of 0. So now we are moving back to state 0. Executing this hello underscore qubit circuit. In the backend, I've given state vector simulator earlier and measuring the result and getting the output in state vector notation. So we use get underscore state vector function and display the output here. And we draw using MPL matplot library over here. Okay, so the output of this is going to be 0 again. So this was our output here. So here I'm creating 2 qubits now. So moving on with 2 qubits. So I'm creating a quantum register of 2 qubits, storing it in a variable called as q, passing my q as a parameter here. So quantum circuit of q, and I'm applying X gate on qubit 1. So look at the draw here. I think I didn't draw it here, maybe it will take time. So so what we'll have is we'll have X on the second line. So Q0 will not have any X, but Q1 will have another X. Executing it, getting the state vector. I want you to note down this output order. Qiskit actually stores in a different notation. So this is 0, 0. This is 0, 1. This is 1, 0. And this is 1, 1. When I mean 0, 0, 0, 1, 0, 1 is actually your right end is your 1. Okay, so Q0 is your 1 and your Q1 is going to be 0 here. So the output of this is going to be, we are having on Q0 we'll have 0 and Q1 will have 1. So the output is going to be 1, 0. So we have a higher amplitude at this place. So 0, 0, we don't have 0, 0, we don't have 0, 1, but 1, 0 gives us the highest amplitude. So 1 plus 0 j, and this is for 1, 1. I'll repeat once again the order. This is 0, 0. This portion is 0, 1. This is 1, 0. And this is 1, 1. So the output of this particular quantum circuit is going to be 1, 1 over here.
Manjula madam, one
Yes.
request is there. The team attendees are asking about the file, the notebook file.
Okay.
Is it possible to upload the file into, I shared one link now in the chat window. Can you upload there into that? If you upload, they can start practicing along with your presentation.
One second. You have uploaded to the chat window.
Yeah, in the chat window I uploaded. There is MyQT knowledge series. Under that folder, there is a folder for your session. Upload into that folder.
One second. Is my screen visible now?
Yeah, yes, madam. You are in the right place.
So this one, right?
Yeah. In this folder, upload the notebook file. Yeah.
Sure.
All of you can download the file from this location.
Once again, where do I have the option of uploading here?
I think you have to send to Deepa. Deepa only can upload.
So
They send to
no, ma'am. This folder is empty, is there, right? You can write it.
No, we are going to upload. No, we are going to upload.
Okay.
Yeah, Deepa will upload now. Madam, send the file to Deepa. Deepa will upload.
Deepa ma'am's mail ID.
I'll send it.
Yeah. Or else you can send it through.
Whatever. KG, shall I send it to you?
Yeah, yes, madam. You can send it to me. Yeah, you send it to me, madam. I will do. Okay. Yeah.
One second. I'll just stop my screen.
Yeah, yes, madam. Also, the deck also share with you, madam. I will upload that.
KG, I'm not having your ID also.
Yeah, I'm sending now. In the chat window, I'm sending, madam.
Yeah, sure.
Yeah.
Yeah, sure. KG, I've mailed you.
Okay, madam. I will take it, madam. You can continue your session.
Okay.
Thank you.
I have one more file that I have in my IBM ID that I'll share it later.
Okay, madam. This is okay. I will download, upload, download. Okay, thanks.
So meanwhile, if you're till getting this file, let me show you this IBM ID actually. So if you're new, you can go for create. I hope my screen is visible. Visible, right?
Yes, ma'am, it's visible.
So if you are new to Quantum IBM Experience, you can create a new IBM ID account here. And once you create, it will show you, you can log in, and it will show you this page. So we have two portions here. One is composer portion, the other one is launch lab portion. So the composer will look like this. I'll come back to this demo a little later. And we also have the lab portion of it. So that also I can show you here. So this is my first demo file. I'm just opening it here. The one which I showed you there also. So let me increase my size here. The first one, earlier portion which I showed here, this is I've installed in my local machine, the same program. I'm executing my code over using my local page. But this thing which I opened right now is actually the same quantum program using IBM Quantum Experience. So you'll have your IBM Quantum, you'll have your user ID, you have all these options over here and your dashboard, everything. We'll just walk through this little later. I'll just finish off this particular program. You can execute it and you can visualize your output. It's the same thing which I showed you till now. I'm showing you. Maybe this is little bit smaller in size. So I can show the same program using my Jupyter notebook in my local machine. So moving on with my slides. So this is 0, 0, this is 0, 1. I hope my screen is visible. This is 1, 0 and this is 1, 1. So we have Qiskit applied to qubit 1 and there is nothing applied on qubit 0. Similarly, moving on, here I'm applying X for Q0 also and Q1. So this is another way. Either you go for X of 0, that will also work, or you can also say Q of 0, that will also work. So it means that we are applying X gate on qubit 0 and X gate on qubit 1. So here you will have 1, 1 as your output. So this is 0, 0, this is 0, 1, this is 1, 0 and 1, 1 is now with a higher amplitude. So remember the travel agency problem. The configuration which is going to be your best one will have the highest amplitude. So here we have the state 1, 1 is in 1 plus 0j. So this is the output of this particular quantum circuit. I'm drawing it using matplot library. So you could see your X on Q0 and X on Q1 also. And executing it using your execute function. So hello underscore qubit is your circuit name, your backend. We have used state vector back simulator here and obtaining the output, and bounce function for displaying the histogram output here. So we could see we are in state 1, 1 for fully 100% probability that we measure state 1. The ordering of qubits is very important. This is 0, 0 is the first one, 0, 1, 1, 0 and 1, 1. Please keep a note. Qiskit uses little Indian problem way of output visualization. What do we mean by that is, this is Q0. The rightmost bit is your Q0 and your leftmost bit is your Q1. Okay, so this is Q0 and this 0 is your Q1. Here 0 is Q0 and this 1 is your Q1. Okay, make sure that you have understood this. So bumping up qubits with 3 qubits here. So I'm going for a quantum circuit with 3 qubits. So my circuit name is 3 underscore qubits, executing using the same backend. And the ordering of qubit now is, the first one is 0, 0, 0. This is for 0, 0, 1. This is for 0, 1, 0. This is 0, 1, 1. And the next 4 is 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Ordering is very important. Right end is Q0. Next one is Q1. And next one is Q2. So Q0, Q1, and Q2. So look at the quantum circuit in the next portion. So we have X applied on Q0. So what will happen? The top line will be X gate, and next we don't have anything. So my output is going to be 0, 0, 1. Understood how I am reading it? My Q0 is 1. Q1 is 0, Q2 is also 0. So we have this particular portion. So 0, 0, 1. And you could see 0, 0, 1 has highest amplitude here. So it is 0 plus 0j for 0, 0, 0. For 0, 0, 1, we have 1 plus 0j. I hope everyone understood this. So this goes for 0, 0, 1 as our output here. Drawing it using our MPN. So our circuit will look like. So for this we have 0, for for Q2 it is 0, for Q1 is 0, and for Q0 we have 1. So you read it as 0, 0, 1. Next is I've applied 2 qubits. Q0 and Q1 we are taking it to be X gate, and this is we don't have. So output is going to be 0, 1, 1. And if you could see this, 1, 1 is highlighted here. So 0, 1, 1. So 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, and this is 1, 0, 1, 1. So this is my output here for this particular quantum circuit. So now the next case is we have X gate on this, and X gate on Q0, X gate on Q1. So your output is going to be 1, 0, 1. And you could see 1, 0, 1 is the third last in our state vector representation. So we have 1, 0, 1 in this particular portion. Any doubts in this first experiment? And we normally use, if we are running any program using Qiskit, we import this, and we also display the version of it. These are the various providers which are available. R is the provider which we are using right now. Aqua, IBM Q provider, Ignis, Terra, all those things. IBM Q provider goes for executing using your IBM Quantum Experience thing. So this is the place where this is the portion which we normally do this for all of your quantum programs. Okay. So my demo on how I can switch to my PPT. Is my PPT visible? No, right?
No, it's not visible. I think you have to share again, then select the PPT window.
One second. So yeah, I think fine. It has come up now.
Yeah, we are seeing now.
Not getting my full screen sharing actually. That is the issue.
Yeah, the entire screen option. I don't know why it is not.
It's not visible. Maybe I'm being invited as a guest. Is that an issue?
I'm not sure.
Okay, I'm not able to go have that option. I'm not able to see the entire screen option actually. So this was a demo on the first one. So how to create a quantum circuit and how to work with state vector simulator, and the output visualization which we saw in the previous example was one was state vector output, the other one was histogram output. So I have not given any classical qubits in this example. I just want you to show how to create a quantum circuit, how to work with qubits, how to apply X gate only. So it's from 0 to 1 and from 1 to 0 how we are moving, and only those things I've showed in this particular demo. Next is the next part of my talk is I'll be moving on with quantum gates. So the first portion I'll be starting off with single qubit quantum gates. I'm not moving so deeper into it. I'll just give you, we have X gate, Y gate, Z gate, S dagger, we have T dagger, and we also have a Hadamard gate. Of these, X gate is the one which we saw right now, Hadamard is again another important gate which I'll be concentrating more on. So I'll just show you the other outputs here. This slide is again a very important slide. You can note down so that you can use it for later on purposes. So your place state, how do I obtain my place status? If I'm starting from gate 0, if I apply a Hadamard gate, I'll move on to state place. Again, if I have my H gate, I can, if I have my input as 1, if I'm applying a Hadamard, it will take me to my state minus. So this again I'll be showing you in my demo. So let me just finish off this particular slides. So your plus state is actually given by 1 by root 2 get 0 plus get 1. Your minus is given by 1 by root 2 get 0 minus get 1. And then we have the y basis, your I and minus I. So 1 by root 2 get 0 plus I1. 1 by root 2 get 0 minus I1 for your minus states. For my X gate, my matrix representation for your X gate is X is actually your your classical NOT gate. So what will your NOT gate do? From 0 to 1, 0 gets inverted to 1 and 1 gets inverted to 0. So the same thing happens over here. So we have, if I apply X on gate 0, it will take me to 1. If I apply X on gate 1, it will take me to 0 state. If I apply X on had a plus state, it retains me in plus state itself. So these I've given the output for all things. For 0, what will happen? For 1, what will happen? For plus, your minus, your I and your minus I. You can note down and you can play on these quantum states later on. So what will happen when you apply X gate on your plus state? That you can visualize it and see. I'll also show some of our demo here. Next one is your Y gate. Your matrix representation for your Y is 0, minus I 0, and the various output visualizations for your Y. Okay, you can note down this Y and you can play when you have time on with your quantum gates. One is Z gate, another very important quantum gate. So it takes you to what does it do is, what does my X do was it inverts. So X is 0 converts to 1, 1 is inverted to 0. What will my Z gate do is, Z will not do anything for 0, but for 1 it will change it to minus 1. So we have a phase change over there. So for 0 it doesn't do anything. For Z on 1 we have a phase change here. So a negative color change we'll have. I'll show you what is phase change later. Similarly, we have another gate called as S gate. So it is 100I, and my various other output visualizations. For 0, what will happen when I apply S for 0 state, S on 1 state, S on plus, S on minus. You can work on these things. A very important one, you can use all of these quantum gates and in your quantum circuits. Basically, your Hadamard gate, your X, Y, and Z are in reversible gates. That is, they have their own inverses. If I find H inverse, we have H itself. But S gate and T gates, they don't have their own inverse. That is why we have this SDG. SDG goes for S dagger, the transpose of S gate. X, Y, and Z, they have their own inverses. So that is X. Again, if I apply X, it takes me back to my original state. Similarly, your H, if you apply H again, it takes back to your original state. But S, the next gate you have to apply is SDG gate to take you back to your original state. Okay, so these are called as X, Y, Z are called as poly gates, and they have their own inverses, and we call them also as Hermitian operators. Okay, these are some of quantum mechanics things. So S gate, and now I'm moving back to the demo of single qubit quantum gates. So I'm just going back, stopping. So I hope my single qubit gates notebook is visible. You can take the second notebook which was being shared. Is this visible?
Yeah,
Yes, ma'am,
we
it's
are seeing
visible.
the notebook. Yeah.
Fine. So I'm again here. I'm taking a quantum circuit of 1 qubit, drawing it, evolving it, and I'm getting state 0 here. So this is your circuit 0. And now applying x on x0, state 0. So we have inverted it. So now it becomes 0, 1. That is your state 1. So for 1, your state vector representation is, your vector notation is this. Now moving on to your Hadamard gate. So I'm just going slow here. So I'm starting from label state vector dot from underscore label, another new function. What do I mean by this is I'm starting with my label called as 0 over here. So by default, any quantum qubit will have a value 0. And we are creating a quantum circuit of 1 qubit and applying, we call that circuit as my circuit. And we are applying Hadamard gate on it. So H of 0. And I'm drawing it using my matplotlib library. And here I didn't use execute function. You can also use execute function and run it out, or otherwise another way of executing this quantum circuit is using evolve. So sv.evolve of my circuit, and I'm printing it, and this time I've used plot underscore state underscore Qisphere. This is another visualization. So what we do is we import it. So from Qiskit.visualization, plot histogram I showed you in my previous notebook. We have the other notebooks, other visualizations. One is block multivector, the other one is Qisphere. Qisphere, and we call this is your block vector representation here. Qisphere is actually 2-dimensional representation, whereas block sphere is actually 3-dimensional representation. So visualization of a quantum circuits in 2D view and 3D view is well supported in IBM Qiskit, and that helps us to visualize in block sphere outputs also. So we have a Hadamard gate here, and look at this. So I told you I'm in state 0 and 1 at the same time. I can show you this demo using my composer here. One second. Let us take, this is the composer view. So I showed you, you can create an IBM ID here and log in using your quantum IBM experience. There are 2 portions here. One is composer portion, the other one is lab portion. So in your composer portion, what we can do is you can open it. So once you open, you get a screen like this where we have various tabs. Here you have all your quantum gates which are available. So as I told you already, we have your H gate, your I gate is your identity gate, and this NOT symbol is your NOT gate. This is your T gate, your S gate, your Z gate, and this is your T dagger, S dagger, SDG I showed you in my PPT. So these are these gates, and this is your measurement. And we have rotation gates also. I'm not touching them for today's session. So various rotation gates are available, phase gates are there, your conditional if statements, you can do anything. If you are not good at programming, or if you are initial state of learning quantum, I would suggest you to use composer rather than notebooks. So if I'm going for a Hadamard gate, so I have a quantum circuit here. You can look into this. So this is Q0, Q1, Q2, Q3, and we have your classical qubits. So we have 4 quantum bits and 4 classical bits here. And this is a QASM code which is dynamically generated. So once if I do any alterations to my circuit, this code will automatically be updated. So here we have created a quantum register for 4 qubits, quantum register for 3 qubits. Say if I don't want any qubit, I'm just going to delete it. So I don't want Q2, I can choose this, choose the delete option, it gets deleted. Can you see? Now instead of Q4, it has been reduced to Q3. I'm again deleting another one. I just want you to visualize it for 2 qubits. So I'll show you for 1 qubit first. So I'm in state 0 here. If I apply a NOT gate, you could just go for dragging it and dropping it. So if I drag and drop my X gate here, it comes over here, and look at this. This code is automatically added, dynamically updated actually. So X gate is applied on Q0. So we have a quantum circuit of 1 qubit and 4 classical bits. If I want, I can reduce my classical bits also by choosing that and choosing minus option, it gets deleted. So I'm just deleting it. So we have a quantum qubit, 1 qubit and 1 classical bit, applying X on Q0. So what happens? We were in 0 state, and now when I apply X gate, I'm moving to 1. Let me apply another X gate here. So you could see we have now moved back. So I can visualize this actually using the visualization. I can inspect it. So I'm starting with this. So initially we are in state 0. So this is your probability of getting state 0 is 100% probability. This is your Q sphere output. We are in state 0. And this is my state vector output. So if you could see, scroll down little, you could see your state vector here. This is for 1 plus 0j and this is for 0 plus 0j. So I'm in state number, I'm in state 0 here. And next one, I'm applying NOT gate now. So what does NOT gate do? Inverts your state 0 to state 1. So probability of measuring 1 is 100% probability. And look at your Q sphere output. The top, if my arrow is pointed upward direction, we are in state 0. If it is pointed down, we are in state 1. And the output here, your state vector output is 0 plus 0j, 1 plus 0j. I hope you are able to find the difference here. So we are in state 1 now. Again, moving on, I am applying my second NOT gate here. So what happens? We are moving back to 0. So we started from 0, that is we were in up direction, applied X gate, we went down. Again, I am applying X gate, I am moving back to state 0. So your state vector notation here, and look at the code which is automatically updated here. So this is what I want to show. So this is one thing. And next is I'm just inspecting, I'm stopping inspecting, I'm deleting this. I want you to go for applying Hadamard gate now. So let me now apply Hadamard gate and show you the superposition states. So we have a single qubit quantum registers. For classical register also we have one. I'm taking a Hadamard on Q0 and look at this now. Earlier when I was applying my X, I was only in state 0 and state 1. But when I've applied superposition, I'm in two states. I'm in both state 0 and I'm in state 1 at the same time. And you could see the probability of measuring state 0 is 50% probability and the probability of measuring 1 is again 50% probability. We are in state 0 and 1 at the same time here. And my output state now, this is actually 1 by root 2 its value. So 0.707 is 1 by square root of 2. I'm in 50% probability of being in the state 0 and 50% probability of being in state 1. So this is how we apply superposition states and create a superposition state. Let me add another qubit here.
Ma'am.
Yes, sir.
Ma'am, what is the effect of classical register here, ma'am?
Right now, I've not measured anything. So if I'm making a measurement, I'll store it in classical bit.
Okay,
I'll show you. Can I show you the demo here?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
And now I'm actually going with Hadamard for 2 qubits. So 0 and 1. Let me take another. Okay, I just don't want to confuse. So I'm just taking 2 qubits here. So 0, 0, 0, 1, 1, 0 and 1, 1. All 4 combinations. So we are in a superposition of state 0, 0, 0, 1, 1, 0 and 1, 1. So it is 25% probability of being in the state 0, 0, 25% probability of 0, 1, 1, 0 and 1, 1. But what if I do a measurement here? So now I'm just measuring one of my qubit and I'm storing it in this. I'm measuring Q0 and I'm storing it in C0. Okay, so what will happen is my outputs visualization. So this can be either 0 or 1 and this can be either 0 or 1. So I'm just measuring one of my outputs, or if I'm adding, let me add another one, another classical bit here, and add a measurement for second one also. So I'm measuring Q0 and storing it in classical bit 0. I'm measuring Q1 and I'm storing it in classical bit 1. So if I go for a measurement, see if I before measure, let us inspect this. So I hope the circuit is clear. So CASM code, we have 2 quantum bits, 2 classical bits, applying Hadamard on Q0, applying Hadamard on Q1. measuring Q0 and storing it in C0, measuring Q1 and storing it in Q1. So initially, we have the probability of measuring all of these is going to be 25% probability because we are in equal superposition state. Let us inspect this circuit. So first state, Hadamard, okay, applying both H. So 0, 0, 0, 1, 1, 0, 1, 1. I'm in an equal probability of all my 4 states. So 0, 0, 0, 1, 1, 0, 1, 1. But when I measure, I'm going to land up in one of them. Okay. After my measurement, I'll either land in 0, 0 or 0, 1 or 1, 0 or 1, 1. Run this experiment for multiple times and you could check out. Okay. So it is not going to be in all of my 4 states. So measurement actually collapses my output. So what is after measurement, my output is not going to be in a superposition state. It will be in the one which has the highest one. Here all 4 were equal probability, so it randomly chooses one. Is your answer clear, sir?
Yes, ma'am. Very well.
So
perfectly. Thank you.
After measurement, we are actually going to land in one of our possible state, the one which has the highest amplitude. Here all 0, 0, 0, 1, 1, 0 and 1, 1 were of equal probability. So we are randomly we are in one.
Finally, when we are measuring with respect to the classical bits, how quantum will help us, ma'am?
See, our entire algorithm, the thing is, you are just going to go with your algorithm, you apply your quantum circuits and go with it. And finally, you are going to have your measurement. The measurement one will choose the one which is going to be the highest thing. In this example, all are equal probability, so I'm just landing in one. But my output of all my algorithms are not going to give the same equal probability of all of my states. The one which what was that? The travel
You mean to
agency.
say that the bit which is having the highest information, that will be chosen as a classical bit?
That will be chosen as your output and stored in your classical bit. So the travel agency problem, if I choose 0, 1, 1, or the other one which we have was 0, 0, 1, right? Both A and B are traveling in taxi 0 and C is traveling in taxi 1, or both A and B are traveling in taxi 1 and C is traveling in taxi 0. So in that case, those two things will only be selected. Either 0, 0, 1 will be selected or 1, 1, 0 will be selected. The other options will go out. Got it?
Thank you. Thank you.
Okay. So the same example, if you're going for 3-qubit one, the travel agency problem for, sorry, I deleted it. For the travel agency problem, you can just go for increasing it. So apply Hadamard on all your 3 qubits. So now if you could see, we are in equal all combinations, 0, 0, 0, 0, 0, 1, everything. I'll just show you classical bit also. Let me add. So it actually gets collapsed, but all your visualizations for all your states, it will show more. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, everything. 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Everything will be there. Okay. All your 8 combinations, your state vector, and your Q-sphere output. Okay. So this shows me that I'm using 3 qubits. So I have 3 inner circles here. One of the question which I got in my cert exam was, they'll give you this, they'll not give you these states. They'll ask you, identify the number of qubits in this quantum circuit. So 1, this is 2, and this is 3. So there are 3 qubits. So that you have to show. So these are the various things you have here. And okay, there is another demo at the last. Let me just move on to my second part of my code. So yeah, this also I thought of showing you. I'll show you this in my composer itself. So now the second part of my, I'm not measuring. I'm just deleting it. You can just go for choosing it and deleting it. So I just don't want 3 qubits also. let me delete one qubit here. So let me have this. And okay, this was for 0, 0, and that is I'm in combination of both 0 and 1. Now let me apply X gate over here. So this why I'm moving here is the second portion of my quantum code. I'm applying X and then a Hadamard. Okay, so this I thought I'll show you in this demo. So applying an X gate and then a Hadamard gate. So let us inspect this. So initially I'm starting in state 0, applying X gate. So now we have moved to state 1, applying Hadamard gate. So what does Hadamard actually do? So it actually converts us to your state minus. So 0 minus 1 divided by root 2. What do I mean by 0 minus 1 divided by root 2? We have a phase change here. Your Q square output will actually give us the phase change output, whereas block sphere, the 3D view, will not give you a color change. Okay, block sphere will give us three-dimensional view of our output, but Q sphere will gives us the 2D view of your output, and we'll also have the phase change notation here. So this is actually 1 by root 2 get 0 minus 1 by root 2 get 1. That was for my state minus state, if you remember the matrix representation over in my slides. So I'm applying, I have my X gate and then I apply a Hadamard, and we are now changed to from state plus. Okay, we are in state 1 and then I'm applying H. So H on 1, where does it take us? H on 1 takes us to state minus. Okay, H on get 1 takes us to get your minus state. Okay, so your minus state notation is 1 by root 2 0 minus 1 I 1 by root 2 1.
Can I consider like X followed by H can gives to P only?
X followed by H leads to
P, that is phase shifted.
No, it's not like that. It takes you to plus state.
Okay.
It's not phase change only. It takes you to your X basis. So there are, I told you 3 bases there, right? We had Z basis where we computed on 0 and 1. But now I'm moving on to X basis where we are going to make computations on plus and minus states. Okay?
Yeah.
So I'll show you that in... This is your Q sphere representation, so 0 minus 1, and this is for the various Y gates. I'm not moving on so deeper into Y gate actually. You can work on with your Y gate. This is all your output visualization. So Y on 0, what will happen? Y on 1, Y on plus. So create plus. So how will you create plus? You have to apply X gate and then a Hadamard, you have to apply a Hadamard gate. It takes you to plus, and then you can apply Y. It will take you to minus I minus. Okay, so you can play with these states later when you have time. All your things, I'll just show you very important things if I have anything here. If I want to create I, okay, I want to create I, that is my Y basis state. So how do I create Y? Let me have with this example. So I'm just deleting. So first is for Y, I'm applying X and then I'm applying S. I'm right, and then I apply Y gate, and then I apply my Y gate, and now let us inspect the sanctions. So I'm starting off. Initially, I'm in state 0. So state 0, applying Hadamard transformation. We are in state plus. So 0 plus 1 divided by root 2. And now I'm applying S. So what does my S do? It does actually, look at the phase state vector here. So it is 1 by root 2 0, and this is 1 by root 2. Actually this goes for your I. Okay, this is your state I. Your I is 1 by root 2 get 0 plus I 1 by root 2 get 1. Okay, that is this particular state. And now I'm applying Y on my I. So what does it do? Your Y output. So Y on I, what does it do? Yeah, sorry. So this is plus state. I'm applying S on plus. It is taking me to I. And now we are having Y on I. What does your Y on I do? Y on I. On top, I don't remember those values. Y on I. Any answers? Y on I? My slide will have my Y on I value. So what will happen for you? Y on I, Y on minus I and all those things. Somewhere right now I saw. Yeah. Your Y on I retains you in your I status. Okay. So that is what we have here. So again, let us inspect. Stop this. Inspect it once again. So add a mat. So 0 plus 1 divided by root 2. Next I'm moving to my S state. So it takes me to my I state. Again, Y on I. It also retains the same I state. So this is your I. So I is 0 plus I1 divided by root 2. So we are in 50% of your state 0 and your I1. Okay. Let me stop inspecting it. So coming to my single qubit gates. So we have all these things. Moving on with my multi-qubit gates, again I have to go back to my PPT, okay, or let me work out with my code itself. So there are, next portion of my talk is multi-qubit gates. So multi-qubit gates, I'm just having a CX gate, C0 gate. What will happen to CX is, this is your control qubit and this is your target qubit. Okay, let me show this demo using so I have my CX here. So what is actually CX doing? Okay. So we have this is 0 and this is 1. Sorry. Once again. I'm having two qubits here. Both are in state 0, 0. So initially both are in 0, 0. What will your C0? C0 is actually a 2-qubit quantum gate. What will it do is it has two qubits. One is your control qubit. The line which is on top, we call it as control qubit, and this we call it as target qubit. So CX is your gate name. If I'm using a composite, your CX, but if I'm using my code, will be again, yeah, we use CX here. So 0, 1. So what does 0, 1 indicate is your 0 is your control qubit and 1 is your target qubit. If my control qubit is in state 0, my target qubit will get flipped. So that is the idea of your CX. If your control, I'll repeat once again, if your control qubit is in state 0, your target qubit will get flipped. So what do I mean by my control qubit in state 0? Now my control qubit is in state 0, my target is also in state 0, so the output is going to be in 0, 0. My input is also 0, 0, my output is also 0, 0. But now I am adding an X gate over here. Add an X gate to your control qubit. Can you see the difference? So what happens here? This is now inverted to 1. This is in 0 state. So if my control qubit is 1, my target qubit will get flipped. So if I'm in 0, 0, my output is going to be 0, 0. If I'm in 0, 1, my output is going to be 0, 1. If I'm in 1, 0, my output is going to be 1, 1. If I'm in 1, 1, my output is going to be 1, 0. So I'll show you all the things. So here initially we are in, let us inspect this.
Ma'am, sorry to interrupt you, ma'am.
Yes, sir. No problem.
Ma'am, I got confused actually.
Once again, I'll do one thing. Better go to my PPT and come back to this. One second. I'm sorry for this. Can you see my PPT?
Yes, ma'am.
So this is multi-qubit gates. we are going to have, this is a 2-qubit representation where we have ket 0. Ket A is represented using 0, 0, 0, 1, 1, 0 and 1, 1. So all 4 combinations. The sum of the squares of your amplitude should sum up to 1. Just as we had in your single qubits, we are also going to have your sum of your squares of your amplitudes is going to be 1. Okay, so sum of A 0, 0 square, all these things is going to be 1. Moving to our C0. So C0, this slide would make you more clearer. So this is my control qubit and this is my target qubit. So if this is 0, my target is going to be 0. If this is 1, my target qubit will get flipped. Okay, so various input outputs. So what we have is control, I'm taking it to my right end and my target I've given it. Read it from right end actually. So if my input is 0, 0, what is my output? 0, 0, will not have any change. 0, 0 means my output is also going to be in 0, 0. But if my input is 0, 1, if my control is 0, 1, so this is 0, the top line is 0, the bottom line is also 1. So control qubit is in 0, so my bottom line is going to be 1 only. So 0, 1 will remain 0, 1. Understood? The third line. 0, 1 will remain 0, 1. But 1, 0. If my control qubit is in 1, if this is in 0 state, what will C0 gate do is, if your control qubit is 1, your target will get flipped. So if this is 1, 0, my output is going to be 1, 1. If my input was 1, 1, my output is going to be 1, 0. Okay, so it operates on 2 qubits. Your Q0 is going to be your control qubit and Q1 is the target qubit, and this is the main quantum gate which is used for quantum entanglement. The circuit for this is, I'm creating a quantum circuit of 2 qubits. I'm applying QC.Cx of 0, 1 and I'm drawing it. My draw will come like this. I've showed you 2 different outputs here. Just forget this now, right moment. Don't worry about this. We'll just go for this. 1 second. So this column is for 0, 0, 0, 1, 1, 0 and 1, 1. Similarly, row wise 0, 0, 0, 1, 1, 0, 1, 1. So for 0, 0, my output is going to be 0, 0. For 0, 1, my output is going to be 0, 1. If my input is 1, 0, my output is going to be, anyone answers? For 1, 0, what is your output? For 1, 0, your output will be
1, 0.
1, 1. And if your input is 1, 1, your output is going to be 1, 0. Okay, so this was the one which I was actually showing there in my so coming back to this portion. So shall I go with this now? Let me stop it out. Let me inspect once again. So I've taken the third case here, 1, 0. So initially we are in this is 1, this is 0. So your remember, Qiskit takes the reverse direction. So this is 1, this is 0. So so we are in 1, 0 here. Moving on, applying C0. So 1, 1. So this was earlier 0. Since my control is 1, my target gets flipped. So we have 1, 1 and your output is 0, 0, 0, 1, 1, 0 and 1, 1. So 1, 1 is in highest probability here. So it is 1 plus 0 J. Let me take this less down. Let me stop inspecting. Come down. So this is your second one. So that is our input is 0, 1. Okay. Your input is 0, 1. Your output is also going to be 0, 1. We are not going to have any change. Okay. If I inspect this, because your control is still in 0, so you will not have any change in your outputs. No change. So 0, 1, we start at 0, 1. My C0 will not do anything. I'll remain in state 0, 1 itself. But if I have an X gate over here also, so this is my last one, fourth one, so 1, 1. So what will happen? So if I inspect this, starting off, we are in, both are in 1, 1. Now C0, so it will have changed to 1, 0 for me. So 1, 0, I'm reading it in this end. So that is, this one remains as it is, and this one, if my control is 1, what happens to my target? My target gets flipped. The target right now was 1, so it now changes to 0. So 1, 0 is going to be our output, and look at this output, you will have 1, 0. Okay, your CX gate, your automatically it goes for it. Measurements, I'm just not going so deeper into measurements right now, because it is going to collapse. Here we are having 1, so if I add a measurement here, we are going to have 1 state only. Add a measurement here for both the states. Let me delete one C3 here. So I'm just CQ0, all those things, everything is fine. Let us go for inspecting it. That's it. So we are having only 1 now. Understood? Any doubts in this? Any doubts, anybody?
No doubts, ma'am. Actually, so many doubts are getting cleared, ma'am. Thank you.
Thank you so much. There are so many other gates. I think I should show you a demo of executing it. I'm moving back to my PPT. I'm skipping off some of the portions. I'm not going so deeper into it. Let me, this is for measure and you're drawing it. All these things, executing it. Yeah, this output is your block sphere output. Can you see my screen? I hope it is visible. For block sphere, we use this plot block multi-vector, and it shows you in 3D view your outputs of Q0 and Q1. For both the qubits, it will show you separately. So 0, 0. We are in state 0, 0. So it shows us this. This is our Q sphere histogram and the various combinations. So 0, 0, 0, 1, 1, 0, and all the combinations. The entire this. I have some more gates here. I'm not going deeper into them. CX, CZ, swap gates. Just have time when you're free. Please go through all these gates because I'm running out of time. I think I have another 20 minutes more. So you just work out. I'll come back to this later if I have some time. I'm just going back to my so this is my PPT. I'm coming back to my PPT. I'll just work through so that all these gates you can work on later. So C0 gate, your CZ gate, what will CZ gate do is, if your control qubit is in state 0, it will not do anything. If my control qubit is in state 1, it inverts to -1. It is exactly to your CX gate, but Z, instead of applying X here, we'll be applying Z gate in CZ. So Z gate, what does Z gate do is, it leaves 0 untouched, but it flips the sign when your qubit is in state 1. So for 0, 0 will not have any change. For 0, 1, no change. For 1, 0 will not have any change. For 1, 1, it will have to be, it will change to -1, 1. So 0, 0. When I mean 0, 0, it is Q0, Q1 are in state 0, 0. So 0, 0, 0, 1, 1, 0 and 1, 1. So 1, 1 alone, my output will be -1, 1. For all other things, we don't have any change. So 0, 0 remains 0, 0. 0, 1 remains 0, 1. 1, 0 remains 1, 0. And for 1, 1, it remains -1, 1. Okay. So this is your CZ gate. Your swap gate, it swaps both the qubits. So 0, 0, 0, it will actually swap your Q0 to Q1, Q1 to Q0. So that is what your swap gate. This is control swap. If my control qubit is 1, here we are going to work with 3 qubits here. If my control qubit is 1, only then swap will be done. If my control qubit is 0, there will be no swap. What does it swap? It swaps Q1 and Q2. Q0 is your control qubit. Q1 and Q2 are the gates which get swapped. So if my Q0 is 0, Q1 and Q2 remain as it is. If my Q0 is 1, my Q1 and Q2 will be swapped. The value of Q1 will go to Q2 and the value of Q2 will go to Q1. We also call C swap gate as Fredkin. Your CX gates are called as Feynman gates. This was a gate which I showed you.
One question.
Yes.
Ma'am, one question on the previous slide. The last one control swap, right? When we have a last entry 111. So in that, it's not going to change any state, but will the energy will get applied there?
It is not going to change any state, but
will there any operation happen? Like the states will.
It'll actually do happens actually. So
Okay,
my input is 111 because my control is 1. The value of this 1 goes here irrespective. See, it doesn't know what value that register is actually having. Right?
Sure.
We'll not know when I'm executing, I'll not know whether it is 1 or 0, but it does do the transition. But since they are same, we are not able to find any difference.
Thank you.
But it does. This was the AND gate which I showed you in my PPT earlier. So this is for if both are 0, 0, nothing will happen. If both there are two controls here. If both the controls are 1, this will get flipped. Okay. So my input for my AND gate classical AND gate will use this. So for 0, 0, 0, 0, 1, it is going to be 0. For 1, 0, it is going to be 0. For 1, 1, it is going to be 1. Any doubts? Anyone is talking there? If both your control qubits are 1, your target will get flipped. The input of target qubit is 0. So if it is 1, 1, 0 gets inverted to 1. Okay, so this is your output. And this is the one which we will be using in your classical AND gate. Any doubts? No? So,
Madam, there are few questions asked some 30 minutes before. One question is, what is visualization seed? Another question is, one is, what is a visualization seed? Sorry, someone can mute.
Friday,
KG, can you ask the question now?
Okay, KG. Okay. KG, please proceed.
Ma'am, actually in the chat box, some guest has asked a question like, what is the visualization seed? I think KG sir was about to ask the same question.
What is the visualization speed? Huh?
Seed.
What do you mean by seed?
Seed. They have given it as visualization seed.
Need?
I think they mean it as seed only.
Visualization seed or need? I'm not able to get your question.
Visualization seed only. Visualization seed. Sorry, I'm back again.
Okay.
If you go to chat window, you can see. But the question is, what is visualization seed? SEED.
I'm not.
I think I can take up this question.
Yeah.
See, actually, it is useful in the state diagram. When you see the probability, that probability is based on a random seed. We can set the random seed in your Qiskit, either composer. Yeah, it is useful in composer only. In the composer window, if you set the visualization seed to number, whoever set the same number, they will get the same histogram output, the state vector output. So that is useful thing to reproduce the same output. If you change the seed, the same circuit will give different output, not drastically different. The probability will be little bit different than different visualization seed. You can experiment it. Same circuit with a different seed, execute the circuit, and then see the state vector output diagram. You will see a different value. And this is useful for quantum simulator only. When you are running on a real quantum computer, it won't have any impact. The visualization seed will not affect your circuit. Hope that answer your question. There is another question, madam.
Yes.
That question is, shall we edit the auto-generated code by Radhamani?
No, it is auto-generated. We can't edit it. Or the thing is, if we edit, automatically the code will get modified.
Yeah, the challenge with auto code, you will choose the format, whether it is Cosm code or Qiskit code.
We can convert. Yeah,
you can convert. Copy the Qiskit code, put into your quantum lab, Jupyter Notebook lab. There you can change, play around. That is how we used to do. We won't try to change in the composer view. We will copy the code, put into lab notebook environment. There we will play around. Indeed, yes, madam, we used to build visually using composer, then copy the code, play around. That is how we build some of the POCs.
I think
turn around.
We can edit. I hope so. We can. You do automatically, or it goes code automatically updates. We can just make a try.
That answer your question. I request all the attendees to turn on your videos. We will take a screenshot, and that will be shared in the social media, such that people will come to know our discussions. Yeah, please, everyone, turn on your videos. And Deepa, we can take a screenshot. I know many people. It is known face. Ramani, Rani. Hi, Rani. That's nice. Deepak, you can take screen, sir. Ravindra, sir, you can come online. Amit, Anders, Dia, Vaishnavi, please. Balamurugan, if possible, you can switch on. But I don't know how your situation is there. Not necessary, if not possible. Whoever possible, please switch on your video. Deepa, you can take screenshot. Cool. That's amazing. This is nice to see a lot of new members attending this session. And we have any other questions? No problem.
Actually, I'm running short of time. Actually,
okay, madam.
Also, but,
yeah, sure. Okay, right. Deepa, you can take a screenshot, right? Have you taken screenshot?
Yes, KG, I have taken.
Okay, right. Cool. Thanks, team. Thank you. Madam, it's done, right, madam?
KG, I just show the demo of executing jobs. Will that be okay?
Yes, madam. Please go ahead, madam. Yes, madam.
I'll just show you executing this. Just deleting. I'm just going to stop it. So we have a certain set of inputs here. I've applied a C0 and we have a measurement. And if I want to run this job on real devices, so what are we supposed to do? Okay, so we are done with it. So it is actually, you can save this file and you can go for. Before running an experiment, you have to add measurements to your code. So this is one. I think we can add code here. I'm applying X again on Q of 0. Say let me do of 1. It will actually reflect it. So it is possible for us to add codes here, as Radhamani ma'am asked. So either you can go with this, or you can drag and drop here. So both works actually. So let us have 1 1, and I'm applying C0. So my output is going to be 1 0 here. So I'm running this experiment in devices or in simulators. So the compulsory portion is you have to have your classical bits and add measurements here. So setup and run, you can choose here. There are various devices available here. So here you can, if you want the things which are the name, the status, the number of qubits, the quantum volume, operations per second, the total pending jobs, all those things you can actually look into it. So IBM, anything which starts with IBM underscore are called as real devices. And simulators, you can also choose simulators here. You can sort them based on any field which you have, and you can also add filters. So filters, if I don't want all, I'm just going for simulators. It will show me all the simulators which are available. So according to your hub, the things which are available. These are the various simulators which are available for public. So there are simulators for 100 qubits or 5000 qubits and so on. If I don't want simulators, I want devices, I can add a filter. I can choose my devices over here. Systems are called as devices. So you could see this is a 7 qubit mission. I'm just closing this. So a 7 qubit mission, IBM Lagos, again 7 qubits. So you can just go for choosing any device and submitting your program. So this is offline, your system status is offline, this you can't choose. You have to check whether your status of your system is online and look at the number of pending jobs which are there for IBM Q Llama. So there are 46 jobs, it is a 5 qubit machine. So like that, you can choose any of your devices or simulators. So if I want my output immediately, it is better to choose a simulator rather than a device. And so let me go for, since it is just 2 qubits, we go for smaller ones. So even state vector, let us choose this simulator underscore state vector and look at this. You choose your hub, the number of shots. So the number of shots you can have 4028 or you can run it for 8024 shots, whatever shots you want. Shots we increase to get outputs to be better ones, and you're running it. So running it takes time to run, but for simulator obviously we will get the output immediately.
Ma'am, what are shots?
Shots is the number of times you run the same experiment. I told you, right? Quantum devices are prone to errors. So we don't run our experiment for one time. We run it for more number of times.
Okay.
We run it for multiple times. So the composer jobs which I have here. So this is the output which was generated. So I could see the details of it. I'll show you the screen for it. I'm going to run the same program for multiple number of times so that I get perfect output, the correct output, because devices are prone to errors.
But will it be the same when we choose the systems, ma'am?
Systems, you will have errors actually. So see, in this example, I have 0, 1 as full 100% since it is a simulator. But for systems, what will happen is you will have the measurement of other qubits also. The frequency count here for 8024 shots, I'm getting 0, 1. Okay, but when I'm running the same program using systems, I might get for 1, 1, for 1, 0, for 0, 0 also. Not the maximum things, but I'll have a minimum number of outputs. You can run it and see the same program. You can submit your job to a device. You could see 0, 0 also, some 0.5%, 5% you'll have the outputs for other things also. But the one which is going to be your output is going to be the maximum one. So for 8024 shots, 8000 shots, I might get 0, 1. But for 100 shots, I might get something else. Like that it goes. It splits. You'll
so
have it.
In the actual system also, we have to give the shots.
Yeah.
Okay.
You have to. Either you're running it on devices. See, for simulators, even if I run it for fewer number of shots, I'll not have issues. I'll get the same output. But if I'm using a device instead of state vector simulator, if I choose a device and if I choose it for lower number of times, I'll get all outputs to be in the similar time. Say I'm getting 0, 1 also for 100 times, 1, 0 also for 100 times, 0, 1, 1, 0, everything it is equally visualized in the sense I can pick up my output, right? So what do? Run the same program for higher number of shots and choose the one which has the highest frequency. The output will be the one which has the highest frequency. Now if I'm running it, I can show you another output of my devices dashboard actually. I don't know whether I have it. Jobs, the various other jobs which you have run. This is this right now I run this. This was executed 3 days back. So the entire number of jobs, which is, it takes
What
time.
will be the waiting period for running on the systems, ma'am?
You can just submit your job and go, sir. So after some time, it just gets executed.
I can take up this question.
Yes.
An average 13 seconds to 60 seconds for non-premium devices, like 21 qubit, less than 21 qubit system, which are available open access. For premium system, that waiting time is less. Sometimes it goes 7 minutes also. Hope that answered your question. Yeah, okay,
Yes,
madam, you
yes,
can continue.
It mostly takes time. Mostly what I do is I submit my job overnight and come back actually. And, sometimes it takes even 2 hours for me to execute. If you are running really,
Okay.
it takes more than 2 hours. Also. It depends on your the code size and all those things. So this was the one which I thought of showing. I hope I'm actually done. Any other doubts? We can just... KG, any other doubts from your side?
No, I think all are great. No questions in the chat window.
I have a one question, ma'am. Assuming that I have a data set and I want to get the computation out of it to choose the higher information feature, then I have to apply a quantum circuit on it. Then how I will choose which the gates will be suitable for the feature or for my data set?
That is the that is the trick.
That is the main thing. But for feature map, you can use ZZ map. Actually, if you are using Qiskit, there is a circuit called ZZ map. That is the right thing for feature principal PCA, principal component that one. Yeah, that will help you to identify features in the QML problems.
So which
ZZ feature map. Yeah, Z feature map. That is the circuit which will help you to identify features from the data set.
Thank you, sir.
Welcome. Yeah, that's a great session. Yeah, Deepa, please.
Okay, hi everybody. Hello, ma'am. Informative and very good presentation. Now I hand over to KG for the vote of thanks.
It's amazing session, madam. It is a pleasant and knowledge we acquired today. It is immense, depending on your presentation, the circuit examples, all are very good. Thanks for your session. We are looking for a more deep dive, maybe in October or September. We request you to conduct another session with more deeper circuits.
Sure. Thank you. Thanks a lot, actually.
Thanks, madam. And for all attendees, thanks a lot for joining us. And next session is on quantum computing career. How to start a quantum computing career by one of the most popular quantum computing professional in the industry. The announcement will come. Please do attend that session also. Thanks for being wonderful audience. We have learned a lot of things from your questions. Thanks to all. Thanks, Deepa. Thanks, madam, and thanks, Pradeep. And yeah, thank you for.
Thank you all for giving a wonderful information session, ma'am. Actually, I learned a lot of many basic information, and also got solved with some of the doubts which I had without asking the doubts. Thank you.
I'm really overwhelmed actually. Thank you, KG, for the opportunity. Deepa ma'am for coordinating entire things. And all the participants, you were really so enthusiastic actually. Thank you all, and hope we'll meet in the future regularly. Actually. Nice, KG. Very good
Thank you.
initiative.
Thank you.
Thank
Bye-bye.
you.
Thank you.
Thank you.
Bye.
Thank you. Bye-bye. Thank
Thank
you.
you,
Thanks to
Casey.
all. Thank you.